last classes we have seen the equivalent circuit of a diode. Today we will be discussing about the rectifier circuit, which is an important application of semiconductor diode. So, basically what is a rectifier? The rectifier circuit is a circuit which rectifies AC voltage into DC voltage. Now, in most electronic applications we will be requiring DC voltage, that is constant voltage supply. Now, in order to get constant DC voltage from the supplied AC voltage, because in our homes we get AC supply, which is power supply, we get alternating current, and so in order to get DC voltage level from AC, we will have to use rectifier circuit where diode is used. So, the DC power supply has different stages, starting from an AC supply, then it will be using a transformer to bring it to the desired level of AC voltage, and then rectifier circuit to rectify the AC into unipolar voltage, and then there will be filtering circuit to smoothen out the pulsating DC voltage which we get after rectification, and then another regulator circuit will be there to finally keep it at a constant voltage level. So, starting with an AC voltage, a steady DC voltage is obtained by rectifying first, then filtering to DC level, and finally regulating to obtain a desired fixed DC voltage. So, if you consider in block diagram form, we have here first stage is transformer. This transformer will be getting the AC supply, which will be given from the power supply at the rated frequency, and in our household devices we have AC supply at 50 hertz. So, this transformer is there to bring the level of this AC input to the desired level by transforming it. So, voltage transformation is done. We can step up or step down the voltage by adjusting the turns ratio in the transformer. Then this rectifier circuit will be having the diode, which will be rectifying the AC voltage to an unipolar DC voltage, and then this filtering circuit will be there. This is an extra circuit which will be required for smoothing out the pulsating DC, and then finally a voltage regulator circuit will be there, which regulates the voltage level even if the load varies. So, finally, this load, that is the output circuit where we want to apply this DC voltage, will be getting the DC voltage, and this DC voltage, as desired, it should be constant level voltage. For this rectifier circuit, we use the semiconductor diode which we have discussed earlier. So, first of all, let us discuss a half wave rectifier. This half wave rectifier circuit will be converting the AC voltage to a unipolar DC voltage, but only one half of the input AC voltage will be available, and in the other half we will get 0 voltage. So, if we now consider a half wave rectifier circuit, the circuit will be having a single diode as such shown in this diagram. So, we have this input voltage which is AC, and let us consider a sinusoidal voltage, which is practically what we get in the power supply, and there will be this resistance. The voltage available across this resistance is named as V naught. So, this voltage, output voltage V naught, will be used for a load. Now, in this circuit, if we consider this diode and this input voltage, we will first of all convert this diode to its equivalent model. Now, as we discussed earlier, its piecewise linear model will be a constant voltage drop V D naught and the forward resistance, average resistance R D. So, these two will be in series with the ideal diode. This ideal diode is just to show the direction of conduction of the current, and this is the resistance across which we will be having the output voltage V naught. Now, this is an AC supply. So, it is in a complete time period T, it will have one positive half cycle and a negative half cycle. Now, whenever you have this V I greater than equal to this V D naught, that is the thresholding voltage, then the diode will conduct. That means, in the positive half cycle of the input AC voltage, whenever we have input voltage greater than V D naught, this diode will be conducting and then the current will be flowing in this circuit. So, if we now find out the output voltage V naught, this output voltage is equal to the current flowing through this resistance R multiplied by the resistance R. So, what will be this current flowing in this circuit? So, we can find it out. This is V I minus this drop V D naught divided by the total resistance in this circuit R D plus R into this resistance R. So, this will be the voltage across this resistance. Now, separating these two terms which are combined by this negative, that will be equal to R by R D plus R into V I minus R by R D plus R into V D naught. Now, practically in such type of circuits, what we get is that the resistance is comparatively very high in comparison with this average resistance of the diode. Average resistance of the diode is in the order of a few ohms only, and we can very well ignore this resistance in comparison with this resistance R, which is R is far bigger than R D. So, if that is the case, that is R D is average resistance of the diode is very small as compared to R, then the denominator in these two terms R D plus R can be approximately written as equal to capital R, because this whole term will be almost equal to capital R, since this is R D is very small. And then this output voltage will have this expression as simply V I minus V D naught, because if we replace this R D plus capital R by capital R only, then these two cancel out in both of the terms. So, we get what? We get V naught equal to V I minus V D naught, and this is nothing but the approximate equivalent circuit of this diode which we have discussed earlier. That V D naught will be now here and this will be ignored, R D will be ignored. So, as R D is ignored, it is nothing but the constant voltage drop model. So, we have that, we can now assume that we are replacing this practical diode by its constant voltage drop model. So, assuming the constant voltage drop model, we can now have this circuit is approximately, we are getting a simplified circuit which will be having only the constant voltage drop V D naught of the diode. So, now when in the positive half cycle of the signal, if we consider, then as soon as this input voltage V I at any point, if we consider the instantaneous voltage V I, whenever it is greater than, in the positive half cycle, whenever it is greater than V D naught, the diode will start conducting. So, the voltage output V naught will be V I minus V D naught, and in the negative half cycle, whenever we get that it is less than 0, that means it is in the negative half cycle, input voltage is negative, and in the negative half cycle there will be no conduction in the diode. So, we will be getting 0 current, and the current is 0, that is why the voltage V naught across R is also 0. So, in the negative half cycle we will be getting a 0 voltage, and in the positive half cycle only we will be getting the output voltage V naught, which is V I minus V D naught. So, if we now consider the input voltage and the output voltage V naught superimpose on each other, then we get this type of curves, voltage waveforms, where you can see here that the output voltage has a difference between the from the input voltage by V D naught. So, V D naught drop will be there across this diode, and so at each point the output voltage is having a difference from the input voltage by the diode drop V D naught. So, these are the input and output waveforms assuming constant voltage drop model of the diode. Now, this output voltage, as we see here, is completely almost this is 0 in the negative half cycle as well. To a little portion inside also it is 0, that is because whenever it is less than 0.7 for silicon, that is less than V D naught, then output voltage will be 0. So, from this point you see that voltage becomes 0. So, basically here one complete time period of the input waveform, if we consider, that is capital T say, then only for even less than T by 2, half of the time period, we have conduction of the diode. But of course, this small region where till when it is output current is 0, that is very small. So, roughly approximately we can say that for half of the input waveform, the output voltage will be 0. Now, if we want to find out what will be the average voltage V naught, then we have to integrate this output voltage waveform within this time period. Now, that we will be doing now to get the average output voltage V naught. So, for that purpose we will be again assuming the diode to be ideal, because as I have mentioned here, that you can see that if I exactly want to find out what is the output DC voltage, then I cannot integrate between 0 and capital T by 2, because it is not exactly that, because for a small portion we see that the current is not there, that means 0 current. So, output voltage 0, but then for all practical purposes, like in a rectifier circuit, we can consider the diode to be ideal, because we are mostly interested in knowing the rectification and do the analysis from that point of view. So, even though we are not exact at this point for integrating between 0 and T by 2, which is not exactly correct, but that we can do so. So, we will be now considering ideal diode. That means, we are further simplifying the model by ignoring V D naught as well as ignoring average resistance of the diode R D. Let us find out first from that approximate model what will be the output voltage V naught, assuming the diode to be ideal. So, that we will be doing now, and for that let us first consider again the input and output waveforms considering the diode to be ideal. So, that will be as shown here. It is the input waveform which is an AC waveform. So, it is V m sin omega t will be the expression for that AC waveform, because we all know that this is the well known expression for sinusoidal waveform of voltage, which is V m sin omega t. Omega is the angular frequency, which is equal to 2 pi f. F is in cycle per second or hertz, and our power supply which we get domestically, that is having 50 hertz as the supply frequency, means f will be 50 cycle per second or hertz. So, now this waveform is input waveform V m sin omega t, and output waveform considering the diode to be ideal is like this. So, now we will be carrying out the analysis with this output waveform having exactly one half cycle the diode will be conducting and the other half the diode will be off. So, we will be getting 0 voltage. That means, we are getting a pulsating DC, this is called pulsating DC, and with one half cycle off. So, let us do that analysis for finding out what will be the output voltage or average DC voltage. So, by VDC I am meaning that the output voltage which is the average DC voltage. So, for finding that out, we have to integrate between this whole time interval 0 to capital T. So, if we integrate in order to find out the average DC voltage, 1 by whole time period T integration 0 to T V m sin omega t dt, because this input and output waveforms have exactly the similar shape, that is a sine wave. So, we can easily integrate it by this ideal assumption. So, this is a simple integration. If you carry on that integration, it will be equal to 1 by capital T V m. Within that integration, if we do that sin omega t integration, it will be minus cos omega t by omega between this lower and upper limit 0 and capital T by 2. Here you have to note that because one half cycle is having 0 voltage, we are to integrate it between 0 and capital T by 2, because the other half is totally 0. So, we are further simplifying it by integrating it between 0 to capital T by 2. So, that will be giving this expression of minus V m by omega can be taken out, omega into capital T, then cos omega t, which is in between the limits 0 and capital T by 2. So, that will be equal to putting the limit, it will be cos omega capital T by 2 minus 1, that is equal to minus V m by, now here we can substitute omega capital T is equal to 2 pi, because 2 pi f is equal to omega, that is that we all know. So, from that 2 pi f is equal to omega, we can now f is equal to 1 by t. So, from that we find out that capital T into omega is equal to 2 pi. So, substituting that here, it will be further boiling down to minus V m by 2 pi within bracket cos omega t, you just substitute by 2 pi by 2 minus 1. So, now we get cos of pi minus 1 in the bracket, that is equal to cos pi minus 1. So, minus 1 minus 1 minus 2. So, finally, we get that is equal to V m by pi. So, in a half wave rectifier, we have the output average DC voltage equal to V m by pi. If you find out the value of 1 by pi, it is 0.318. So, 0.318 V m will be the average DC value of the half wave rectifier. Here in the half wave rectifier, we have seen one disadvantage or one drawback of half wave rectifier is that in one half of the input waveform, the output voltage is totally 0. That means what? We are not getting this output wave or output voltage for one complete half cycle of the input waveform. So, this is not exactly what we want. So, we want that the output voltage should be a constant DC level. So, we will be going to another advanced rectifier which is known as full wave rectifier. So, it will be rectifying the whole input waveform, that is the full wave will be rectified. That means, in both the half cycles we should get rectification. So, that is full wave rectifier, which has advantage over half wave rectifier, that we are going to discuss now. But before that, we would like to know what will happen if we consider a practical consideration of diode drop of 0.7 volt. So, now if we consider say silicon has a diode drop of 0.7 volt. So, now output voltage will be Vi minus that drop. So, in output voltage V naught, if we find out in this analysis whatever we have done using ideal diode, here instead of Vm we will have to put Vm minus 0.7 for silicon, or if germanium it is 0.3. So, that drop will come within the bracket Vm minus V d naught. So, finally, our expression for VDC or average voltage drop at the output, the DC voltage will be equal to 0.318 Vm minus Vt, Vt meaning the threshold voltage or the diode drop or Vd naught as we have named it. So, approximately we can write that output voltage DC voltage is 0.318 or 1 by pi into Vm minus Vt. Now, there is another important term to know, that is the peak inverse voltage of the diode. Peak inverse voltage, as we have mentioned or discussed earlier, it is the maximum or peak voltage that the diode can withstand when it is not conducting. That has an important analysis, because in order to not enter into the breakdown, we must always remember what is the peak inverse voltage of a diode, because in the reverse bias condition, if you recall, when the reverse voltage is greater than the breakdown voltage, it will enter into the breakdown and it will be suddenly rising. But in all practicalities we do not have, or we should not overcome that peak inverse voltage. So, in this case, if we consider this circuit again, now when the diode is not conducting in the negative or negative half cycle of the input waveform, then what will be the voltage across it? So, that is the peak inverse voltage, and you can very well see here it is nothing but the peak voltage of the input wave, that is Vm. So, Vm is the PIV of this half wave rectifier circuit. Now, we will be considering a full wave rectifier, which will be a better rectifier than a half wave rectifier. So, full wave rectifiers has different configurations or circuits, and let us consider first a bridge network, that is bridge full wave rectifier. Having a bridge of or a network of diodes, there will be 4 diodes as arranged in this configuration, as we can see here. So, there will be D1, D2, D3, D4, 4 diodes. Now, the input Vi is an AC waveform. Let us consider sinusoidal. Now, if we consider a positive half cycle of the input waveform, then the conduction of which diodes will be taking place? The diodes which will be forward biased, those diodes will conduct. So, we will be applying say this input voltage having Vm sin omega t. Now, output voltage that will be obtained across this resistance R, which is V naught, and it is denoted by this polarity. This side is positive, this side is negative. So, now when it is positive, in the positive half cycle of the input voltage waveform, the red colored straight line will be showing the conduction of the diodes. The diodes D2 and D4, as you can see here, will be forward biased. This is positive connected to P, as well as this is also forward biased, this diode. So, that is why the current part will be shown by this red line. The current will be flowing through D2 and D4. So, across this resistance R, this current will produce a voltage drop V naught. So, as it is a resistive drop, it will be following the input voltage waveform in shape. Of course, there will be a time lag in order to start the current because of this the threshold voltage of the diode. Practically, this will be the waveform. And in the negative half cycle, when this lower point is positive, upper point is negative of the input voltage waveform, then the green line will be showing the conduction of current, because the diodes D3 and D1 will be now forward biased in the reverse negative half cycle of the input voltage. So, the current will be flowing in this direction, that is through D3, then through R, and then through D1. So, the output voltage for the negative half cycle is this one. So, we get for both the positive and negative half cycles of the input voltage, we get output voltage across this resistance. So, it is better than the half wave rectifier that we are getting both the half cycles, we are getting output waveform. So, in this case, if we want to find out what will be the output voltage or DC voltage, again we have to do the integration. But here, of course, while doing the integration, as we have output waveform for both the half cycles, the integration will be, if we do 1 by T by 2, integration will be from 0 to T by 2. That means, we can take 1/2 of the input waveform and we can integrate it. It will be similar for the other half also. So, this integration will finally give, if we do this integration, put down the limits, and as well we find out that omega capital T is equal to 2 pi. So, again substituting, we get finally the output voltage average value is equal to 2 by pi into Vm. This value is exactly twice that than the output voltage which we got in half wave rectifier. So, the average output voltage in a full wave rectifier is twice the average output voltage in a half wave rectifier, that is 0.6366 times Vm, Vm being the peak voltage of the input. So, here also for doing this analysis, we have assumed ideal diode approximation. Now, if we consider a practical diode having cut-in voltage of Vd, then we have the average value 0.6366 Vm minus 2 Vd. Now, why 2 Vd will be coming? Because if we see the current part, the current will be flowing through in the positive half cycle, it will be flowing through D2, then R, then D4. Now, there is a drop here, there is a drop here also. So, 2 voltage drops will be coming into the picture. So, the diode drop Vd will have to be multiplied by 2, that means Vd plus Vd. This 2 Vd will have to be subtracted from the peak value of the input waveform to get the output voltage wave, and that will have to be multiplied by, of course, this 0.6366. So, for a practical diode, we have this is the average value. Now, again if we find out the PIV of this half full wave rectifier for each of the diodes, peak inverse voltage of each diode, you can find out when the diode is non-conducting. When one diode, if I consider when it is non-conducting, what will be the maximum voltage that is across it, that is the peak inverse voltage. So, if I consider say positive half cycle, then this D2, D4 are conducting and D1, D3 are non-conducting. So, what will be the voltage that will be applied across this D1, because D1 is non-conducting? That can be found out if we consider the two ends of this D1 diode. What will be this voltage? Now, again applying if Kirchhoff's voltage law through this mesh, then this voltage drop is nothing but Vi minus this drop, because this is one end and this is the other end. So, this drop is equal to V I minus this drop, that is V I minus V D naught. So, peak inverse voltage of each diode, you can see for other diodes also, when they are non-conducting, the same PIV will be getting, which is equal to V M minus V D naught. So, now here also we are not nearer to a constant DC voltage even now, because what we are getting is a pulsating DC voltage, like this is what we are getting, but then we want to get a constant voltage. Now, this is not obtained till now. Now, we have to now modify the circuit, or we have to add something extra to get exactly a DC voltage. So, for that we will be going for another circuit, that includes the filter circuit, but before that I will be discussing another type of full wave rectifier, that is center tap, using center tap transformer. So, full wave rectifier using center tap transformer. Now, this transformer is a device which can transform or which can convert the voltage level. Input voltage level can be stepped down to a lower voltage level, or it can be stepped up depending upon the turns ratio of the primary and secondary winding of a transformer. So, here a center tap transformer has the secondary side tapping at the center, that means this portion of this, or the upper portion of this secondary winding will have equal voltage to the lower portion. If this is Vs, this will be also Vs, and this is center which will be grounded. Exactly equal voltages we get at the secondary, that is a center tap transformer. Its tapping is at the center of the secondary. So, in this full wave rectifier, this transformer which is center tapped is used to bring the desired to the input voltage to its desired value. We use this transformer. So, here there are two diodes D1 and D2. Circuit is like this. We are getting the output voltage across this resistance, which is V naught. So, now the conduction will be taking place when this is positive, upper point is positive with respect to the center, upper one diode will conduct, and when the center is positive with respect to this, that means this one, this lower one, if we consider, if this is higher, at a higher potential than this, then this way the diode will conduct, but the resistance through which the current will conduct, in both the cases it will be in the same direction. So, that the polarity of the voltage which we get across this resistance will be in the same way. So, input voltage is V I and output voltage which is obtained across resistance will be pulsating DC, as we are getting here. For each half cycle you will be getting the voltage across this resistance, and what will be this peak inverse voltage across each diode in this case. So, if we consider this secondary side voltage Vs, then Vs is having a peak value, say Vm, then when this diode is non-conducting, that is in the case when this upper diode D1 is conducting, then the voltage across this two ends of this diode will be how much? The total voltage across is secondary minus this drop. So, if one half is Vs and peak value of one half is Vm, then total voltage peak value will be 2 times Vm. So, 2 times Vm minus Vd naught, that will be the peak inverse voltage in this center tap transformer, which is a full wave rectifier, but here we are employing 2 diodes instead of 4 diodes in the bridge rectifier. Now, in order to smoothen out the output voltage, we will be employing a capacitor, that is a capacitor filter will be applied to smoothen out the DC voltage which we are getting without capacitor. That means we will have to get a constant DC level without any ripple, but till now whatever we have got in half wave rectifier and full wave rectifier is unipolar voltage, no doubt, but it is not purely DC. So, to get an ideal DC voltage, we will be employing a filter circuit using a capacitor. Now, what will be achieved using a capacitor, that we will have to see in the circuit. So, let us first consider half wave rectifier. So, half wave rectifier with capacitor filter will be this circuit where a capacitor is included across this resistance RL, load resistance. Now, here of course, we will also consider ideal diode for simplicity. So, because we are concerned about the analysis, so let us consider an ideal diode where the cut-in voltage is 0 as well as the average resistance is also 0. So, now in the positive half cycle, when this upper point is positive with respect to the lower point for the input voltage Vi, the diode will conduct as it is forward biased and it will be charging this capacitance. So, the capacitance will be charged and this diode is having 0 resistance. So, the time required for charging the capacitance is almost 0, because instantly the capacitor will be charged, there will be no time lag. So, the capacitor will be charging to the peak value of the input voltage instantly, and this will be Vc will be the output voltage. This voltage across RL is nothing but the voltage across this capacitance. So, if the input voltage is Vi, output voltage if we draw for a particular resistance RL, say we are considering, then it will be first of all charging, the capacitor will be charging to the peak value of the input voltage. Now, when you notice the input voltage, it is sinusoidal, it is varying with time. So, from the peak value it is falling off. Now, if we consider a capacitance, the capacitance has already charged to the peak value Vm, but after this point, peak point, input voltage Vi is going down, but then if we consider the diode, this cathode and anode, on the cathode the capacitor voltage is being applied and the anode is the input voltage. Now, the capacitor voltage is Vm peak value, but the P side anode is having Vi which is less than the capacitor voltage after this peak point. If we consider this point, for example, here the capacitor voltage is V naught which is equal to Vm, but at this point the input voltage is falling down. So, this diode will be reverse biased and it will not be conducting. So, this circuit is off. So, now what will happen? The capacitor voltage will be discharging through this resistance RL. So, that is why this discharging is taking place, shown by this green line. This capacitor is discharging through this resistance RL. Now, this discharging rate will be dependent upon the time constant, which is RL into C. So, if we have a bigger time constant, it will take more and more time to discharge. If we have lower resistance, RL is a small value, then the time constant will be small. So, it will be falling off very soon. That means the rate of discharging will be very fast. So, here the capacitor is discharging and discharging, but you see that input voltage is now at this point increasing here, and after this point input voltage becomes higher than the capacitor voltage. So, input voltage is higher means this the diode will be again forward biased. So, from this point it will be again forward biasing the diode, since Vi is greater than Vc, and the conduction of the diode will be taking place, and therefore, the capacitor will be charged, again charging will be taking place. Again after this point input voltage is lower than the capacitor voltage, so discharging will be taking place. So, charging and discharging will be going on, finally giving a voltage which is having a ripple. It is not a constant voltage, but it will be having a ripple. So, this type of voltage you will be getting. Now, if we go on increasing the resistance RL, ideally suppose so big that it is almost equal to infinity, then of course there will be no discharging at all and we will be getting a constant voltage, which is of course not practically, it is not true. We cannot get an infinitely high voltage, but we will be getting more and more towards DC if we go on increasing the RL resistance, load resistance. Capacitor is not changing, capacitor we are fixing. Now, how much value we should choose that the time about for the time constant, that is time constant should be such that it should not decay appreciably when you consider the time period of the input voltage. So, if the input voltage has a say time period capital T, then this time tau, which is the time constant for the discharging circuit, it should be sufficiently large compared with this time period of the input voltage. Then only we do not see much falling off of the output voltage and output will be almost constant like a DC. So, you have to choose this capacitance the resistance RL value sufficiently larger to have a larger time constant. Now, if we consider the diode conduction, how much time the diode will be conducting? The diode is conducting for a very small time, only for this portion. So, the diode current is such that flowing for a very small time and then it will be becoming 0. So, it is called a surge current. So, if we consider this half wave rectifier and see the conduction of the diode current will be like a surge, it is suddenly it is increasing and then within a very short time it will be falling off also to 0. So, this diode conducts for a very small time, that is why it is called a surge current. Say for example, if we consider the whole time period, only for a small portion T1 it is conducting. Now, if we consider our power supply which has a 50 hertz frequency supply, the time period will be 1 by f, 1 by 50 hertz gives you 20 millisecond. So, the time constant of the discharging circuit in the rectifier should be reasonably high compared to T, means we should choose value of tau very greater as compared to 20 millisecond. So, it should be sufficiently high so that we get overall almost constant DC voltage. It should not fall off drastically. Similarly, if we consider full wave rectifier with capacitor filter, there will be a capacitance which will be connected in parallel with the load resistance. So, here better approximation to DC will be obtained, because if you consider the input voltage which is rectified in full wave rectifier in both the half cycles, again we are getting a discharging and charging phenomenon here. So, overall if we consider the output voltage what we get across this resistance which is V naught, it will be like this waveform, it is like a ripple. This ripple voltage is because of this charging and discharging phenomena. This voltage is called ripple voltage, which is between one lower point, this is the lowest point and this is the peak point. So, in between these 2 points this voltage is known as V ripple, peak to peak. So, this V ripple peak to peak is a measure of how effective your rectifier is. The better and better rectifier will be having lower and lower ripple. So, the measure for this ripple factor is given by a factor R, small r, which is the ripple voltage in RMS divided by average DC value, that is called the ripple factor. So, you should get a low ripple factor if you are interested in making a better rectifier. Now, what will be the output DC voltage finally we will be getting after this capacitor filter being included? To know that, as an approximation is done by considering the ripple voltage to be triangular voltage. So, that here actually if we consider a triangle, if we consider a ripple voltage and assume it to be triangular, it will be like this type of voltage. So, this triangular voltage, if we consider and find out the DC value of the output, V naught DC will be peak Vm minus this drop, that is the minus this Vr divided by 2, Vr peak to peak divided by 2. So, V ripple peak to peak divided by 2 is done to get the average DC value, which is here shown by this black line. So, the average DC value is this peak value minus V ripple divided by 2, assuming triangular ripple. So, that the output DC level will be flowing towards the middle of this triangular voltage. So, it will be triangular voltage. So, the average DC level is through the middle, that is why Vm minus Vr peak to peak by 2 gives you the DC voltage for this full wave rectifier with capacitor filter. Now, if we consider the whole conduction and non-conduction of the diode is conducting only for a very small portion, that is for a very small time t1, and it is non-conducting, and it is only because of discharging of this capacitor that we are getting the output voltage. It is for say capital T2. T2 is the non-conduction time, T1 is the conduction time, and the whole time for this half wave rectifier is T by 2, that means half of the input voltage time period. So, without much violation, we can assume that T by 2 is equal to almost equal to T2. Because this T1 is very small, we can approximately say that T by 2, the whole time from this point to this point, half of the time period of the input voltage, that is equal to the non-conduction time T2. If we assume that, we can now find out an important relation, because during discharging, if we consider what will be this output voltage waveform, we know from capacitor discharging formula that the output voltage for a discharging capacitor will be given by the peak value into e to the power minus t by capital R capital C. This is the time constant, RC is the time constant. Now, at the end of discharging, as you can see, when it completely discharges, when it completely ends its discharging period, it comes to this value. From this value, it falls down to this value. So, this voltage is nothing but the ripple voltage peak to peak. So, we can write here that this at the end of discharge interval, Vm minus Vr, which is the output voltage, because if we see here the voltage which will be finally will be getting after discharging in this voltage. What is this voltage? Vm minus V ripple. So, Vm minus V ripple is equal to the voltage after this discharging period, that is equal to Vm into e to the power minus t by 2 divided by RC. Here I am using that approximation again, because RC is very greater than T, then we can write down this expression e to the power minus t by 2 RC equal to 1 minus t by 2 RC. This power series, exponential series, e to the power minus x equal to 1 minus x plus x square by factorial 2, etc. Here, if x is very small like this, in this case this t is very less as compared to RC that we have assumed, only then it will be practically a good rectifier. So, in that case only keeping up to the first order, that means up to 1 minus x we can write, and others because square of the smaller term will be more and more smaller. So, we can ignore this term. So, it will be approximately possible to write this e to the power minus t by 2 RC equal to 1 minus t by 2 RC. So, now putting down this value here, we get Vm minus Vr equal to Vm into 1 minus t by 2 RC, we have approximated for this exponential term. Then we get Vr equal to Vm t by 2 RC, Vm cancel. So, this term will be remaining, and we know the time period is equal to 1 by frequency. So, we can write now Vr, that is the ripple voltage, equal to Vm by 2f Rc, replacing T by 1 by f. So, now what is this expression? This expression actually gives a relation between the ripple voltage and the peak input voltage and its frequency and the time constant. So, from this analysis we can again find out the average DC value also, because if we look into the capacitor, it is discharging at a constant rate of current of IDC say, then when discharging it will be losing the charge equal to current into time, that is IDC into T, that will be the charge lost by the capacitor while discharging. So, the change in the capacitor voltage because of this discharging is IDC into T2 by C, that is charge by capacitance, that will be the change in the voltage. A change in the voltage is what? Change in the voltage is nothing but the ripple voltage VR. So, VR is equal to IDC into T2 by capital C, again assuming the same thing, that is T2 equal to almost equal to capital T by 2 or 1 by 2f, then we can write down ripple voltage equal to IDC divided by 2fc, replacing T2 by capital T by 2, which is equal to 1 by 2f. So, this becomes the ripple voltage expression, and so we can write about the VDC, DC voltage or output average voltage equal to Vm minus Vr by 2 that we have just now derived, and now substituting for Vr by this expression, we get output DC voltage equal to Vm minus IDC by 4fc, this 2 will be making it 4fc. So, this relation gives you the expression for output DC voltage to the IDC value, peak value of the input voltage, frequency of the input voltage and capacitance. Now, from this analysis basically we have seen different type of rectifiers, half wave rectifier, then full wave rectifier, then half wave rectifier with capacitor filter as well as full wave rectifier with capacitor filter. Now, when you do not use capacitor, we were getting the output voltage as unipolar DC, but it had ripples, like it was not perfectly DC, it was unipolar, it can be said to be pulsating DC, it is like a pulsating DC, but then this is not a good rectifier. So, we had to use a capacitor filter to smoothen out the pulsating DC, to make it more and more nearer to a perfect DC voltage. So, for that, after introducing the capacitance in both the half wave rectifier and full wave rectifier, because of the charging and discharging phenomenon taking place in the capacitor, we were getting a ripple which will be making it more like a DC voltage. We had a DC like voltage, not exactly DC till now, also it is not perfectly right to say that it is DC, but it is more DC like voltage with of course a ripple on it. So, this ripple will be actually determining how much rectification we are being able to get. If we get more and more higher and higher ripple voltage, that means it will be not a good rectifier. If this ripple voltage can be made lesser and lesser, so that we get flatter and flatter output voltage which will be more towards a DC level ideally. So, we will be getting a better and better rectifier. So, in order to do that, we should choose the time constant of the discharging circuit R into C judiciously. So, for that we have to see what is the input voltage frequency, and that will be giving you a measure how you will be choosing the capacitance value, that is input voltage frequency will give the time period. So, compared to that time period, we must have the RC value or time constant considerably larger, so that the overall effect is not seen in the output voltage. Overall effect of this discharging is not clear, or it is not very much drastic that we can achieve by choosing a higher time constant. Now, we can do one example. This example is a center tapped full wave rectifier. This circuit is a center tap transformer having 2 diodes. So, this is the full wave rectifier. So, in this circuit you have been told that it should deliver 0.1 ampere and 15 volt average to a load. This V naught should be 15 volt average, and the DC current which will be delivering to the output load is 1.1 ampere. Now, the ripple voltage is to be no larger than 0.4 volt peak to peak. That restriction is given. Input signal is a 120 volt RMS value, root mean square value is given of the input voltage at 60 hertz frequency, and diode drop is 0.7 volt. And you are to determine the required turns ratio of transformer and the diode peak inverse voltage rating, and ignore diode forward resistance. So, in this circuit, now try this example. Here a center tap full wave rectifier is shown, which is to deliver 0.1 ampere and 15 volt average to a load. Now, the ripple voltage is to be no larger than 0.4 volt peak to peak. It is given to you that it should not be greater than 0.4 volt peak to peak. Now, the input signal Vi is 120 volt RMS at 60 hertz frequency, diode drop is given as 0.7 volt. Now, you have to determine the turns ratio of the transformer and the diode PIV. Now, you have to ignore diode forward resistance. So, to solve this problem, let us do again draw again the circuit. It will be having a transformer in the input circuit. It is a center tap transformer having voltages Vs and Vs in the secondary, say this point is positive with respect to this point, ground, this point is positive with respect to this point. And now, you have 2 diodes, D1 and D2, and this is the capacitance across R. This voltage is V naught. Now, this average voltage DC voltage is given as, it is 15 volt. Now, what is this average voltage? We know Vs max, this voltage minus Vd naught minus V ripple. We have got this expression for full wave rectifier along with capacitor filter. This is peak to peak. Now, assuming triangular ripple, we have analyzed it. So, Vs max can be found out. So, Vx max is V naught average plus Vd naught plus V ripple peak to peak by 2. Put down these values, whatever is given, V15 volt it is, this is given as 0.7 volt, and V ripple is not to be larger than 0.4 volt. So, we take this maximum value. So, this gives 15.9 volt is the Vs max. Now, you are to find out the transformer ratio. This transformer ratio is a N1 is to N2, number of turns in primary to number of turns in secondary, the whole secondary is N1 is to N2 is called turns ratio. You have to find turns ratio. Now, for that we must know what is the RMS value, because RMS value and peak value, there are generally two ratings are defined, are denoted. So, if you want to find out the transformer ratio N1 is to N2, so N1 is to N2 is nothing but N1 is to N2 is nothing but V input by V in the secondary, whole secondary is having 2 Vs, but both must be either RMS or peak. So, let us take the RMS value, this 2 must be in conformity. If you take RMS, both of them must be RMS. Now, this Vs max we know. So, what will be Vs RMS? Vs max by peak value by root 2 is RMS value. Vs max we have found out 15.9 by root 2, that is 11.24 volt. So, turns ratio can be found out, N1 is to N2 is Vi RMS by 2 Vs RMS. The whole secondary, if we look into, the whole is 2 Vs. So, this will be primary voltage by secondary voltage. Now, primary voltage is given as input voltage is 120 volt RMS. So, 2 into 11.24 Vs RMS, that gives you 5.34 as the turns ratio. Now, PIV of the diode can be found out. If we look into the circuit, what will be PIV? 2 Vs peak value minus this drop Vd naught will be the peak inverse voltage of the non-conducting diode. So, PIV is 2 Vs max minus Vd naught. So, 2 into 15.9, Vs max is 15.9 minus 0.7 volt drop is given to you 31.1 volt. So, this is the PIV and the turns ratio we have found. So, in this way we can solve this problem, and whatever you do, you must assume either the constant voltage drop model or ideal diode. So, in this example it is given that it is constant voltage drop. So, we can be proceeding like this. So, in today's class we have discussed about rectification, which is an important application of diode, which you will be finding useful in all electronic circuits, because electronic circuits require a DC voltage mostly to be applied, and that can be obtained by a power supply after rectifying a AC voltage source.